The LI for this lesson is to be able to understand and use Newton's third law to solve problems involving pulleys, and this is the final section of chapter 10. So the most important thing about a pulley is that we are always going to be considering pulleys where there is a light, inextensible string over a smooth pulley. And all of these assumptions means that the tension in the string on either side of the pulley will be the same. And that's what's going to help us to be able to resolve most of the problems that we have. So in example 13, we've got two particles and they're attached at the ends of a light and extensible string and over a smooth pulley of mass 2m and 3m. So if I just draw this out, here's my pulley and I've got this particle hanging down which is of mass 3m, so that must be particle Q, and then another particle hanging on the other side which is mass 2m. And the pulley will probably be connected to some sort of ceiling in some way. We're not too bothered about that. So this is going to be here mass P. So if I start drawing on some of the forces, easiest force to put on first is going to be the weight downwards. So here the weight coming down from mass Q, well, it's got mass 3m, so the weight is 3m multiplied by g, that acceleration due to gravity. And similarly for here, for P, we've got 2m and multiplied by g will be coming down. Then in the string, we will also have the tension. So the tension is acting in the opposite direction to the weight downwards here. We've got these tensions acting. And actually, the way the tension works, we'll actually have the same tension coming down in this way too. There'll also be some sort of force up here. We're not going to really bother too much about that, but just the force that's keeping the pulley up there. And thinking about the motion then, mass Q is clearly heavier than mass P. So we're expecting that mass Q will drop and therefore mass P will go up. This string is inextensible, so as mass Q moves, mass P must move as well. Mass Q is the heaviest, so it will be accelerating downwards, whereas mass P will be accelerating upwards. And the first part says write down the equation of motion for P. So I'm focusing on mass P then. And we know that the resultant force is equal to the mass times the acceleration. Well, here the acceleration is upwards, so I'm going to resolve upwards. If I'm just focusing on mass P, I'm just focusing on exactly on the forces that are going on here in mass P. So the force upwards is the tension. Take away the force that we've got going downwards, which is 2mg. Now we do know that g is 9.8. I'm just going to leave it as g now, it's a bit neater. And that's equal to the mass, well, the mass is 2m times the acceleration. And that's all I need to do. That's my equation of motion for P. And part II is the same thing, but for Q. So focusing just on mass Q, again, I know that the resultant force is equal to the mass times the acceleration. This time, the acceleration is downwards, so we should resolve downwards. Well, I've got 3mg downwards, take away the tension acting upwards here, and that's going to be equal to the mass 3m times the acceleration. And so there's my equation of motion for mass Q. Now for part B, it wants me to find the acceleration. And the acceleration will be the same for both of them because that string is inextensible, they're both moving the same amount, they're moving by the same acceleration. And what I've actually got here is a set of simultaneous equations. If I say this is equation 1 and this is equation 2, if you cast your mind back to solving simultaneous equations, if I want to solve for the acceleration, I want to get rid of the tension here. So I'm going to add equation 1 and 2 together. If I add this left-hand side to this left-hand side, I've got t minus 2mg plus 3mg minus t. Well, straight away the t's are going to cancel each other out. Then I've got 3mg but a minus 2mg, so I'm just going to end up with 1mg on the left-hand side. If I add the right-hand side, it's a bit simpler. 2ma plus 3ma gives me 5ma. Well, clearly my m's are going to cancel there. So I've got g equals 5a, which means that a, the acceleration, must be equal to g over 5, or 1 over 5g. And if you wanted to, you could also do 1 over 5 times 9.8, which will give you two significant figures. So that will be my acceleration. I'm probably going to focus on just the 1 over 5g. I think it's a bit neater. Here, obviously, some rounding's been involved. Okay, part C then says find the tension in the string. Well, this is nice and simple. If I look back to equation 1, I've got tension. If I take that 2mg to the other side, the tension is equal to 2ma plus 2mg. And I know that A is 1 over 5g. So if we sub in that there, 1 over 5g, then I get that the tension is equal to 12 mg over 5. If you've got your calculator, you're just doing 2 times 1 over 5 plus 2. That'll give you 12 over 5. So that is what my tension is equal to. Part D then is asking about the force exerted on the pulley by the string. And for this, I'm just going to do a quick sketch of this top section here, of what's going on with my pulley. So here's my pulley, which is somehow attached to the ceiling. And here's the string. And I've basically just cut the string because I'm caring about the forces that the string exerts onto the pulley. And what I've got is I've got a tension in this side and a tension in this side. And I think from looking at that straight away, you can see that the force the string puts onto the pulley is just equal to 2 T's. So the force on pulley from string equals 2T. And we've just worked out what T is, so we want 2 of those, which is 24 mg over 5. So that's my force on the pulley from the string, 24 mg over 5. Okay, now E is saying, find the distance moved by Q in the first 4 seconds. So remember, Q is moving downwards, P is moving upwards. So I want to find how far Q has moved in 4 seconds. And it says, assuming P does not reach the pulley. Because obviously at some point, eventually, P will hit the pulley here and all sorts of crazy things will start to happen. We're going to assume that the string is so long that P doesn't hit the pulley yet. So, in the first 4 seconds, here we're going to use our TBAT equations. S is what we're trying to find out. We're trying to find that distance. U, well, in the question, we're told that the system is released from rest. So my initial velocity is going to be 0 meters per second. V, I don't know. A is the acceleration, which is 1 over 5g. Or we could use 2 if we wanted to. I'm going to put 1 over 5g. I don't really like rounding too much. And T, we're looking in the first 4 seconds. So I'm going to use S equals ut plus a half a t squared. S, well, u is 0, so that bit's gone, plus a half times the acceleration, which is 1 over 5 times 9.8, times t squared, which is 4 squared. And so I get that the distance is 15.68, which is 15.7 meters. And that is the distance that is travelled in those first 4 seconds by Q. And the final part of this question is part F, which says, state how you have used the fact the pulley is smooth in your calculations. And that's just part of the assumption we talked about up here. So, tension in the string is the same on both sides of the pulley. And that's my assumption. Okay, going on then to the final one, which is example 14. And this is a pulley question, but it's not the same as the last one. And if we read this question, you'll see why. So, 2 particles in B, mass 0.4 and 0.8 kilograms, connected by a light inextensible string. This is where it gets a bit strange. Particle A lies on a rough horizontal table, 4.5 meters from a small smooth pulley, which is fixed at the edge of the table. The string passes over the pulley and B hangs freely with the string taut 0.5 meters above the ground. A frictional force is opposing the motion of particle A and the system is released from rest. So let's just draw a sketch of what's going on. We've got A is lying on this table here. Here's A. And that has got a mass of 0.4 kilograms. This is particle A. Then you've got the edge of the table, and the string goes from A over this pulley on the edge of the table and down to another mass B, which is hanging freely. And the weight of mass B is 0.8 kilograms. So that's what my situation is like. Let's start putting some forces on. So easy forces to start with are the weights. So we've got 0.8 G hanging down from B and 0.4 G hanging down there from A. Now, we also know we're going to have the tension, so we've got a tension here in the string, and just like before, the way that tension works, we'll have another tension here. And again, it's a smooth, inextensible string, so therefore we know that the tension will be the same throughout. The pulley is smooth as well. Now, we've also been told that there is a frictional force that is opposing the motion of particle A. So at 0.08 G, opposing the motion being a frictional force over here. I'm going to add one. Now, when it's released from rest, we know that it's going to start to accelerate, and B is quite heavy here. It's going to be moving downwards. A is going to be moving to the right, opposite to this frictional force. So let's put on our accelerations. B is accelerating there, and A is accelerating over there. And those accelerations will be the same, again, because it's connected by a light inextensible string. So the first part says, find acceleration of the system. This is going to be the same as part A in the last question. So first I'm going to focus on particle A. And I know that the resultant force equals the mass times the acceleration. The acceleration is moving to the right, so I am going to resolve to the right. Well, the force to the right is the tension. Take away this frictional force that's going, so take away 0.08 G. And that's going to equal the mass, which is 0.4, times the acceleration. Now I'll do the same thing but for particle B. Again, resultant force equals mass times acceleration. Here the acceleration is moving downwards, particle B, so I need to resolve downwards. So I get 0.8 G is my force downwards, minus T, this force upwards here B. And that is equal to 0.8 A. There are my two equations, and they are my simultaneous equations. And I want to work out the acceleration. So I'm going to, just like before, add equation 1 and 2 together. E, add minus T, cancel them out. So then I've just got 0.8 G minus 0.08 G. So that's going to give me on the left hand side 0.72 G. Then on the right hand side, 0.4 A plus 0.8 A is 1.2 A. Resolve that and I get that A is equal to 0.6 G. So all I've done there is 0.72 divided by 1.2, 0.6. So there's my acceleration, 0.6 G. Now, the next part is asking for the time taken for B to reach the ground. Well, I'm going to be using my TBATs for this. I know the distance ground. It tells me a question that B is hanging 0.5 metres off the ground. So the distance that B needs to travel is 0.5 metres. U is going to be 0. Again, the system was released from rest. So 0 metres per second. V, I don't know. A is the acceleration we've just found, 0.6 G. And T is what we're trying to find at the time that it takes to reach the ground. So I'm going to use F equals T plus a half AT squared. S is 0.5, U is 0, so that bit disappears. I've got plus a half times 0.6 times 0.8, because that's G, times T squared. I'm not going to bother resolving all that, you do that. I would end up with T equal to 0.412, or round that to two significant figures, 0.41 seconds. So that's the time it takes for B to reach the ground. Now the hard part of this question is part C. It's finding the total distance travelled before travelled by A before it comes to rest. Now what you might think is, if you imagine this system, if I've got the ground is over here underneath it, if I imagine what's going on, I've got A and B, they're moving, and B hits the ground. What you might think is that A stops, but that's not actually the case, because A will be moving. It's not just going to suddenly come to a stop just because B has stopped. The string will go loose, but A will carry on moving until it stops. So let's just think about that situation. If I draw a bit of a picture, here's my table again. By this point, B has just hit the ground, and A has been moving along the table. Here's my pulley. Well, at that moment that B hits the ground, the string will suddenly go a bit loose. I'm going to draw it as a wavy line. There's no more tension in it. But A doesn't just stop straight away. It'll have a bit of acceleration still pulling it, still going, until it comes to a stop. So what I need to do first is I need to work out speed that A was moving at the moment that B hit the ground. And that will actually be the same as the speed that B was moving at the moment that it hit the ground. So I want to work out what this V is here. So I'm going to use V equals U plus AT. V is equal to U is 0 plus A is 0.6G times by T, which is this 0.412. So I get that V is equal to 2.42487 meters per second. And I'm going to highlight that just in a slightly different way. So that is the speed of A the moment that B hits ground. Let's have a look at the forces going on here. So I've still got that resistance force of 0.08 G acting here on A. I will still have the weight downwards. I've not got any tension, but A is still moving, so I'm still have that acceleration there. So let's resolve the forces going. Remember that is still 0.4 kilograms. So if I resolve those forces, I know that resultant force is equal to the mass times the acceleration. Acceleration is to the right, so I need to resolve to the right. So I get that, well, there's no tension, so just minus 0.08 G is equal to the mass 0.4 times the acceleration. Resolve that, and I get the acceleration is equal to minus 0.2 G. I'll sort of highlight that. So we know that from its start position, A starts off by moving 0.5 meters because B also moves 0.5 meters and it hits the ground. However, at that moment that B hits the ground, A still has a bit of distance that it will travel before it stops. I want to work out what distance is. So this is the moment B hits the ground. At the moment B hits the ground, A is travelling with that speed we just worked out. 2.42487 meters per second. That's the speed that it's travelling at the moment B hits the ground. It'll carry on moving until it comes to a stop. So we're trying to work out how far it's moved until it comes to a stop, so when speed is 0 meters per second. The acceleration we've just got is minus 0.2 G meters per second squared. And the time we don't know. So I've all of these things and I need to work out the distance. So I'm going to use V squared equals U squared plus 2S. V squared. And I'm working out S, so I'm going to do V squared minus U squared over 2A. You sub all these numbers into there, you will get that the distance moved by A is 1.5 meters. So from the moment that B hits the ground, A still moves another 1.5 meters. So that means the total distance moved by A equal to, well, firstly it moved 0.5 meters. That's just a normal movement from when B is travelling to the ground. It's 0.5 meters. Then once B hits the ground, it moves another 1.5 meters. So 0.5 plus 1.5. So the total distance is 2 meters. That one is quite a tricky one. There's lots of things to be thinking about. Okay, now you've gone through these two examples, you should be able to go at exercise 10.